4, 3, 2, 1. We're live. Okay, so everybody, welcome to the first Frosty Drew Observatory Public Stargazing Nights Live. We're going to start tonight by letting everybody know that even though we've done extensive testing of this platform, you guys are definitely all of our beta testers. And we are experiencing some very interesting situations tonight, including COVID-19. No, I'm sorry, including including weather. It's raining at my location in Providence.
Go live, and I'm going to give a 10-second countdown, all right?
And
are you guys all ready?
One of you guys got to turn your mic off, okay?
So 10.
So we got some rain, but I'm going to talk a little bit about how we're going to do tonight's setup. So we have 3 astronomers on tonight. Myself, Scott McNeil. We have Derek. He is in Connecticut. And we also have Sean, who's in Connecticut. These are Frosty Drew Astronomers that you guys have all met. And they have been working their butts off with me to get this working. Tonight, our session is being moderated by Jessica, who, if you've been to Frosty Drew before, you've met her at the greeter station. She's a supervisor of our Stargazing Nights program. And we also have Lindsay super moderating tonight as well. And she also is one of our sky evangelists who works at the greeter station during the summer Stargazing Nights at Frosty Drew. We have a substantial amount of images that we're going to show you guys tonight. We're going to try to show what we can in the sky live, but it really depends on how weather works out for us. Though this week we've been doing a significant amount of data collection in preparations for this broadcast, as well as working from home in general. So we're going to be able to present a lot of that data as well. So I'm going to start off by showing some images of Venus that we captured earlier this week. This video was captured about 2 days ago. So this is largely what Venus would look like tonight. All right, here we go. So looking at Venus, well, wait a minute, that's not right. What is this? What the heck? All right, hang on one second. Technical difficulty, right? No, I'm not an advocate for Pluto. So Pluto wasn't demoted, Pluto was promoted, but we're not going to get into that right now. Hang on a second. Real planets, yeah, right. Okay, so hang on, here we go. Switch back over to
Did we lose Scott?
It does look like we lost him.
Oh, maybe he's coming back.
Don't forget you're on mute, Jessica and Lindsay, so we can't hear you. Okay.
This is... All right.
Yep, you guys are gonna have to bear with us because we're learning, much like you guys. And we lost our director for the night.
Yeah, and maybe the live stream as well, since he was hosting the live stream.
I can check it to see if it's still up.
Jessica or Lindsay, is the live stream still up? Oh.
We can't hear you guys.
The live stream's still up. I see you talking.
Okay.
Eric's on now.
All right. Yeah, there's a little delay between this our group chat. And
We're learning, much like you guys.
yeah.
And we lost our director for the night. Lindsay,
Oh, boy.
we can hear the live stream echo.
Hosting the live stream.
Uh-oh.
What? I can check it to see if it's still up.
Where'd the chat go?
Jessica or Lindsay is live. All
Hey,
right.
there you go.
So while we wait for Scott to come back, the idea tonight was we were going to show you guys some images that we've taken in the past. Scott had some data from this week. Sean and I have some data from previous imaging sessions. You know, could be years ago, could be earlier this year, maybe last year. I don't know if Sean wants to go first, or if I can brave my connection and see if I can stream something.
Sure, I'll try to go first.
All right.
Bear with me. So I have 11 images in a slideshow that I've captured previously, since tonight's weather is not cooperating with us. I'm going to end up talking about those images that I captured. Hey, Scott's back.
And he's muted.
And he's on mute. Scott, you're on mute. There you go.
Better. It's a laptop crash. Sorry about that.
Sorry.
Maybe it's getting rained on. I think that might be it.
That could be it.
Continue, please.
Okay, so I'm going to go over some of the images that I've captured, talk a little bit about how I've captured them, my setup, etc. Like I said, I got 11 of them. So let me get that up. All right, cool. My window is not there.
And I could switch over anytime you want if you need to.
Well, let me see if I can get it. All right. Can you guys see my screen?
Yep.
All right. So the image that you guys are seeing should be M51. Is that correct? That's displaying correctly?
Yes, we do see.
Okay, so M51, I caught this a few years back using my Newtonian reflecting telescope. It's a face-on spiral galaxy, and it's got some pretty cool features in this image. You can actually see some really faint galaxies. Can you guys see my mouse?
Yep.
Okay, so it's some faint background galaxies. There's all this pink and reddish color you see in here is a lot of activity, a lot of star forming activity in this galaxy. I don't know how many light years across this one is. Scott, maybe you can add to that, the size of that.
Oh, yeah. Messier 51, we're talking about, I mean, it's comparable. The primary galaxy, the spiral, is comparable to the size of the Milky Way galaxy, which is about 100,000 light years across.
Okay. It's also got a little bit of an interaction here. You can see a small satellite galaxy that is interacting with the main M51. And because of that, you can see some dust. We call it the E or the 3 formation. There's some dust being thrown around. Also, the main M51 galaxy is being stretched out slightly because of the interaction with the galaxy. It's quite a neat target to both image and observe. Depending on the size of the telescope, when you take a look at it, it can look from anywhere from a fuzz to actually you noticing spiral features, arms and such. This one's located in the Big Dipper, Ursa Major, right near the handle of what you would call the Big Dipper. I don't have much else to add to this, Scott. Anyone
An
else?
interesting thing to note about Messier 51 is that this is a galactic merger that we're observing here. So the primary galaxy, 51, which is a face-on spiral that you see, where you can see the bright center, you can see the spiral arms coming off. That galaxy is starting to interact with that much smaller galaxy. And the smaller galaxy is starting to become very disturbed by this interaction. Now, this is a really important point because this is what's going to happen to us here in the Milky Way. In about 3.5 billion years, I'm going to miss it. I don't know about you guys, but we're going to have a merger with the Andromeda galaxy. And when you think about a barred spiral galaxy like Messier 51 here, or like the Milky Way galaxy, it's really aesthetically pleasing. You got the bright center, you got the bar, you have the spirals that come off the bar. But from a position of efficiency in the galaxy, star formation, it's really rather a terrible time. We experience a substantial lull in the amount of star formation when you have this type of organization. And it's because all those molecular hydrogen clouds are organized along these spiral arms. And you need these molecular hydrogen clouds to mix to trigger star formation. Now, when this galaxy mixes with the smaller galaxy, as you see in the view here, or when Andromeda and the Milky Way start coming together and merging, you're not going to see so much of planetary collisions and stars crashing into each other. I mean, there's a lot of space in between things. But what you are going to notice is that all of that organized matter in the galaxy is going to become disturbed. And all of the molecular hydrogen clouds in one galaxy are going to start mixing with the molecular hydrogen clouds in the other galaxy. And you're going to see an intense increase in star formation, resulting in a galaxy that we call a starburst galaxy. And from a little bit of a existential standpoint, all of our atoms are borrowed. Our atoms predate us, and they will continue on after we die. And all of our atoms are going to be part of this process when the Milky Way does this. And in a sense, we are the distant ancestors at that point of a new world in a new galaxy. And this is one of the many things about astronomy and the cosmic perspective that makes me feel big.
So Scott, we had a question here from Charlene that says, what happens when galaxies interact?
What happens when galaxies interact?
Yes.
She may have asked a question before I just explained all that, but I believe that I answered that. But thank you, Charlene. You want to move on, Sean? Or you want me to take over? Derek, what's up?
We can keep going with what Sean's got.
Yeah, we got a little taste real quick of 27 up next, and I definitely would like to see that.
That was my bad. All right, so the Dumbbell Nebula. This was actually a collaboration with another astronomer named, I'll give him credit, his name is John Landrino. So this is a narrowband image I captured with him using my telescope for the hydrogen alpha. He used his telescope for the oxygen band, and then we both merged the two images in post-processing software. So this is a planetary nebula, and it's an excellent example, I believe, what our sun is going to do when it reaches the end of its life. That's correct, right, Scott?
That's right.
So you can go ahead.
What we're looking at here is stellar demise. When you think about the Milky Way galaxy, you're talking at least 200 billion stars, at least 200 billion. And of all the stars in the Milky Way galaxy, 97% of them don't have enough mass to actually undergo a supernova. So what results in that is what you're seeing on the screen right now. It is a star that starts to collapse in on itself, releases its outer layers, its photosphere, its chromosphere, its radiation zones, its convection zones, as a gas cloud around the star, and it exposes the core. And the core is no longer fusing, but the core is very hot, and it's radiating a substantial amount of infrared light or infrared radiation into its outer gas cloud, which used to be the outer layers of the star, and it ionizes it. When that ionization process, you blast off an electron and you got an ion floating around, then you got an electron floating around, they want to reconnect. When they recombined, they get excited. Like, yay, we're back together, rock and roll. And when they come back down, they release a little bit of energy in the form of a photon, and we can see it. And that's exactly what we're witnessing in this image that Sean and John had captured. And this is a taste of things to come again for the sun. In about 5 billion years, the sun is going to undergo this same process. And you hear things like 5 billion years, and you think to yourself, wow, that's really quick. That's like tomorrow, right? I mean, these are huge timescales. And when you think about stellar evolution, galactic evolution, these happen on these types of timescales. But this stage, this process of stellar demise, where that outer gas cloud glows, only lasts for 10,000 years. And 10,000 years sounds long to us because we don't live that long. But compared to 5 billion years, compared to the 10 billion year lifespan of the sun, that's a momentary. So it's a very fast process that occurs. What remains after this is done is just a white dwarf star, which is the core of what used to be that fabulous star that is just cooling off.
Any other comment? I got more.
No.
I got more images.
Yeah, show us some more, Sean.
All right. So this one's interesting. Can you guess what this is, Scott?
I'm going to go with that as the Heart Nebula.
Yes, it is. It's the center of the Heart Nebula. There's another nebula kind of inside of it. I forget what the name of it is, but that's what this was supposed to be. I was working on another collab with John and this object, and this is a hydrogen alpha channel, just hydrogen alpha of the heart, the center of the Heart Nebula. Now, the Heart Nebula is huge. I forget if I shot this with my new telescope, my old telescope. Nevertheless, my field of view is actually rather large on my telescope, and the Heart Nebula is comes out, and it's very big. So this would have taken a couple different panes to put together of the actual nebula. I can't remember how many sub exposures I have, but for the duration of my exposures, they're about 2 to 3 minutes long with a cooled CMOS type camera. On this one, I removed almost all the stars because it makes for easier post-processing. There are some stars that ended up getting left behind, but
Fallacy.
What's that?
No, I didn't say anything. That was the rain part.
Yeah, huh? You're shorting out over there. So it makes it a lot easier, and then you can add them back in after. But I actually like starless images. They look really cool, really smooth, really peaceful. It's pretty neat. Now for the scientific perspective, Scott, you can explain a little bit more.
So the Heart Nebula is quite, as Sean was saying, it's quite large. You know, we're talking about an object here that has a distance of 7,500 light years, and yet it can still fill up the frame of your CCD camera. This object spans 165 light years in diameter. Now, let's just stop and think about that for a minute. You hear light years a lot in astronomy, and it is a measure of distance, but more so it's a measure of time. And when I feel like the term is tossed around very loosely, like, oh yeah, that's 1,000 light years, or that's 2.5 million light years to the Andromeda galaxy, or in this case, 7,500 light years. But a good way to think about a light year is 1 light year is the distance that it takes light to travel over the course of 1 year at the speed of light. Now, the speed of light is equal to 186,000 miles per second. And 1 light year is equal to about 5.9 trillion miles. But an even better way to think about a light year is when you're looking at an object or anything in the natural world, or even the synthetic world, you're looking at photons that are emitted by a source, and they enter your eye, and then the photoreceptors on your retina process that energy and convert it into an energy that your brain can understand. And that's how we see things. So you see things as they look when the photons left the object, when the light left the object. Here on Earth, that delay is so small that you don't notice it. But when you start talking about light years, 1 light year, it takes 1 year for those photons to reach your eye. So you see it as it looked when the light left. So your view of something that's 1 light year distant is also 1 year in the past. When we're looking at the Heart Nebula here, your view of this nebula is 7,500 years in the past. And to see what it looks like tonight, you would have to wait 7,500 years. So from a perspective of what this nebula is, you're looking at hydrogen gas along what we call the interstellar medium, which is just the plane of the galaxy, the matter and material that is in the galaxy. And in this case, it's being ionized by some very bright stars that are in the nebula. A lot of times you have a nebula that's passing through a cluster of stars or an area of bright stars, and those stars ionize the nebula the same way we were looking at in the previous image when we're looking at stellar demise. And sometimes you have a hydrogen gas cloud that starts to interact with other hydrogen gas clouds, or starts interacting with another hydrogen gas cloud, or high mass stars, or supernova remnants, all of which will trigger star formation. And that star formation will also ionize the gas cloud via the emissions of ultraviolet light. And that allows us to see it. Now, as Sean was mentioning, this image was captured in hydrogen alpha wavelengths. And that's kind of a geeky term, but if you think about the electromagnetic spectrum, you're talking radio waves on the low energy side, all the way up to gamma rays on the really high energy side. And that's humongous. But there's this little tiny sliver right in the center that's called the visible spectrum. And that's what we see with our eyes. And the visible spectrum is made up of light that's measured in nanometers. And you're talking nanometers, you're talking about the width in between the lines, or the signal lines, or the cosine that you would see in the wavelengths of the light. The low energy side that we can see, which is on the red side, we're talking about 400 nanometers all the way up to about 700 nanometers. And when we're looking at the hydrogen alpha wavelengths, we're looking at the other way around. The smaller 400 nanometers is on the blue side, and 700 nanometers on the red side, the wider wavelengths. We're talking about hydrogen alpha. We're on the very edge of the red part, or the low energy side of the visible spectrum. And we're looking roughly at about 685 nanometers. Now that's a lot of geek for you guys right now. I don't really think that you're going to walk away and say, I'm looking at 685 nanometers of light here. I'm awesome. But it's important to note this because we're capturing very specific detail in this nebula that you wouldn't see if you were just standing there in front of it looking at it. Because a lot of the brighter wavelengths of light, like starlight, would overpower your view.
All right. Thank you.
My cup is empty, so I'm just going to talk a lot to compensate.
That's all right. I appreciate it. You help fill the gaps that I don't, of knowledge that I do not have. Ready for more?
Yeah, let's see some more.
All right. So this is my latest and the one I'm probably most proud of. This is also hydrogen alpha. You can kind of see a theme here. Image using my newest telescope on what's called the Horsehead and the Flame Nebula. Now, this is an object that's in the Orion constellation, so it's more of a winter object, and it's rather faint, but it's very picturesque. So the brightest star you see right above the Flame Nebula is the leftmost belt star in Orion. So it gives you kind of some perspective on where this object is. Again, nebula, so ionized gas. It's in the hydrogen alpha spectrum. There's a famous NASA image out there of the Horsehead Nebula, where the Horsehead is this tan, very focused tan colored. It's rather nice. So I'm happy to have captured this. I have to gather a little bit more data so I can make it a color image, but we're losing Orion this year, so that won't be this year. Scott, you got more science?
Yeah, so that image, if I didn't know Sean, I would have said he stole that.
I stole it. You got me.
But I know that Sean is a fabulous imager, and he seems to play himself down a bit, but don't believe that. He's lying to you. Sean is brilliant. So when you're looking at the Horsehead Nebula here, there's a lot going on in this image. You're seeing not only the left star in Orion's belt, which is Alnitak, but you're seeing a very large piece, or a very important piece, of what we call the Orion molecular cloud complex, which takes up almost the entire constellation of Orion. Now, when you look at Orion with your naked eye, you kind of miss out on a lot of this, because what happens is you get the bright starlight, and your eyes are just not very good at resolving that red light. But by isolating, again, the hydrogen alpha wavelengths, we're able to really capture a lot of these details. So looking at this image, on the left, right just below that bright star Alnitak, you have what we call the Flame Nebula. Now, the Flame Nebula is, again, it's a hydrogen gas cloud, and it is being ionized by the bright starlight that's coming off of the star Alnitak. And if you kind of turn your head to the side and take a look at it, it looks like you're looking at a flame. You have bright areas and you have dark areas. Those dark areas that you see, those are regions that are actually closer to us in that hydrogen gas cloud than the star Alnitak. And the part of that nebula that's being ionized by Alnitak is on the other side from what we see. So the side that we see just appears dark and dormant, and we call that a dark nebula. And that's important to note when you're looking at the Horsehead. And this is why it's so hard to observe the Horsehead when looking in a telescope, because the Horsehead is a dark nebula. And the way you see it is because it's silhouette by those very dimly lit wisps of hydrogen gas that is being ionized beyond it. Now, when you look in the image, you can see them wisping kind of vertically behind the Horsehead. And they cause the Horsehead to stand out amongst that view. Though this is all part of a much larger process, which also includes the Orion Nebula. You want to switch over to somebody else real quick, Sean, or what's up? Derek, you got anything? You want me to take over for a bit?
Yeah, take over for a sec. Hold on.
Yeah, if you could run it for a bit. I'm putting something together because several of the things I had picked earlier in the night were already shown by Sean.
Okay, I'm going to switch over real quick here. And let's see if my laptop crashes again. If it does, yes. So I'm going to show a clip of Venus. So right now, relinquish your feed, Sean.
Walked away.
Yep, there he is.
Sorry.
You stop presenting.
Yeah.
There we go. I'm just going to keep saying it that, yeah, you're good. That this is a learning experience for us. You know, we go by the philosophy here that the more we make mistakes, the more we're learning. Every mistake is actually a lesson. So tonight really is just an educational session. So, you guys see this, Derek?
We saw it earlier. Yeah, I can see that.
All right. So this here is Venus. This is, when we're looking at Venus, Venus is all the rage right now. We're in a time of the year where Venus has now ended up on the left side of the sun from our point of view. We call this eastern elongation because it's on the eastern side of the sun as it relates to our sky. And this is Venus swinging around the sun and coming into a position where we start seeing part of the daylight area and part of the nighttime area. Now, the reason we see Venus in phases is because Venus is closer to the sun than we are. So to look at Venus, you have to look towards the sun. Unlike Jupiter or Mars or Saturn, which are a lot farther from the sun than we are, those objects, you would see them cross the night sky in the south in the middle of the night. Venus is never going to do that from our point of view because we always have to look towards the sun. So we're either going to see it at nighttime in the west, right after sunset, or we're going to see it in the east, right before sunrise. Currently, it's in sunset. And to see Venus in its full phase, you would have to look at it right past the sun because that's when it's on the opposite side of the sun as we are. Now, as Venus is making its way around the sun, it's reaching a point that we call inferior conjunction, which is when Venus arrives in between the sun and Earth. When we look at Venus, we see tonight about maybe 45% of the sunlit area, and we see about 55% of the side of Venus that's in nighttime. And that's why we see what looks like almost a half moon. And we call this the waning crescent phase because it's getting smaller. Now, as we continue to watch Venus over the next 2 months, it's going to continue to wane further and further and further. Though Venus is also going to continue to get brighter in the sky. And that's because it's getting closer to us as this happens. Now, eventually, Venus is going to start to drop down on the horizon again. And around that time is an awesome time to be looking because Venus is going to get super thin. We're talking like a 3 to 4% crescent phase. I mean, it's fabulous to look at. And then after that, we'll lose Venus for about a month, and then we'll start seeing Venus in the morning sky. Venus has the term the evening star or the morning star. Currently, Venus is serving as the evening star. And anyone who's been reading our Facebook or has been reading anything on social media about astronomy has definitely heard all the rage about how Venus has been just rocking socks with the Pleiades this past couple weeks, putting on their celestial dance. We call this a conjunction. Scientifically, it means absolutely nothing. But from an aesthetic or an observational point of view, it's beautiful and it's stunning to observe. And it gives us a reason to step outside and enjoy the night sky. So if you guys got questions about anything we're talking about here, please post them to the chat feed, and Jessica and Lindsay will send them to us. And even if the questions come in after we talked about the object, we're fine with it. You know, we'll do it. We'll deal with it. Additionally, like everyone else who's dealing with the current situation, Frosty Drew Observatory has been, as a result, closed. Largely what happens is the park that we reside in is no longer open to the public. And we're all volunteers. We all have day jobs. And we're here because we love what we do. But Frosty Drew is having trouble surviving right now because of these issues. Because we can't actually have people come to our site. And that donations box we have on our site, that helps us substantially in paying our bills, in keeping our equipment functioning, and allowing us to continue to present live or free stargazing on site year-round on Friday nights. Even though we're not open to the public right now because of the current situation, we are working our butts off to get this stuff working. And as you can see by how quirky this is going tonight, which may just be a product of us being geeks, but I'll chalk it up as because we're learning. Derek, Sean, and I have been working very hard at getting this presentation working tonight. So please, you'll find a link in the description below the live stream to our donations page on our website. It's frostydrew.org/donate. Anything you can donate to us is awesome. And we love you for doing it because you're allowing us to stay open, to present for free, and give people an escape right now from the reality that they're dealing with, and also give people a place to escape to once we open up again and are able to really rock the sky at our location. So
there was a question here from Christina, and she said, when stars are created in nebulas, do the nebulas contribute matter to the formation of stars? If so, would nebulas change shape over time after creating many stars?
Yes. What's her name?
Christina.
Christina, that's an excellent question. So what happens when stars forming nebulae? So what I'm going to do is I'm going to throw up some data sets here on the most popular nebulae that we see this time of the year. And it's called the Orion Nebula. The Orion Nebula is the closest site of massive star formation to the solar system. And it is a fabulous object. And we've learned so much about star formation from looking at this object. So give me 1 second and I'm going to load this guy up. Now, when we look at nebulae and we see the star formation occurring and all this stuff happening, there is a substantial amount of changes that occur in that hydrogen gas cloud. And a lot of these changes happen because of the stellar winds that are coming off of those young newborn stars. Here we go. Slideshow. Give it a second here. I'll load that up. Okay, so think of it this way. So this here is the Orion Nebula. In the Orion Nebula, we have roughly about 700 stars that have already formed. There's enough mass to form somewhere around 2,000 stars. And you see a lot of wispiness in this field. That wispiness is a direct result of star formation. So in the center of the nebula, you notice that it's really quite bright in here. You have a lot of very bright stars in here that tend to be really lighting up that area. Now, this is what it would look like if you could look at it from a much lower. Oh, come on. Bear with me, guys. Learning experience. We would normally be tethering right now, but it's still raining at my location. So when stars are forming in a nebula, they're taking that hydrogen gas, and that hydrogen gas is dropping into gravity wells that form inside the nebula from disturbances. Anything that disturbs space-time. So a good way to describe or think about gravity is a dent in space-time, which is the fabric of space. When you create a dent inside these molecular clouds, all that hydrogen starts dropping into that little gravity well. Now, gravity plus mass equals heat. And when you get enough mass, hydrogen, that drops into that gravity well, temperatures in the core start to increase substantially. And eventually, the temperatures increase to the point where fusion kicks in, and you start fusing hydrogen atoms to helium atoms. Now, when that happens, you have a substantial amount of energy output that happens, but gravity pulls it back in, and you get a balance. This is a newborn star. But that star has stellar winds. That star will continue to gather, or accrete in this case, additional hydrogen gas, and mass will increase. When you get really high mass stars that form, there are intense stellar winds that blow out from those stars, kind of like the sun's solar wind. And you're talking about a constant output of energy in the form of plasma and magnetism. This starts to blow all the gas away in that gas cloud. The more of these stars that form in the nebula, the more of the gas cloud that starts to blow away. And eventually, once you reach about roughly 2,000 to 3,000 stars in these molecular hydrogen clouds, they'll end up blowing all the gas away. And what emerges is a new cluster of young stars called an open star cluster. And all of that gas is now blown back off into the interstellar medium. So not only does it change the shape of the nebula, it completely takes the nebula apart and pushes it back into the interstellar medium. And from an efficiency standpoint, you're talking about roughly 10% of that mass actually goes towards star formation. So it's rather inefficient. Now, in this shorter exposure here of the Orion Nebula, you can see that the center of that nebula is where we have the highest mass stars. You know, these stars are called the trapezium stars, and they are responsible for all that wispiness that you see. Now, unlike the images you're looking at from some of Sean's images, these images are straight off the camera. So if we were doing a live session tonight, if it wasn't raining, now I have my gear set up out here with trash bags over it, which is that, I think that right there really tells the story of New England astronomy, right? But they would look just like this. This is what it would look like. Now, the Orion Nebula, while we're looking at it here, let's talk a little bit about this. Now, this is star formation here. The Orion Nebula is one of two naked eye visible star-forming nebulae in the northern hemisphere. That means that you can see this when you look up at the sky. And I would wager that almost every one of you that are tuned in tonight have actually seen it looking up at the sky and didn't realize it was a nebula. So when you're looking at the constellation Orion, everyone knows what Orion's belt looks like. And underneath Orion's belt, you have Orion's sword. When you're looking at Orion's sword, you're seeing what looks like three faint stars that are somewhat perpendicular to Orion's belt, just a bit off axis. The center star in Orion's belt is the Orion Nebula. And if you look at it, the next clear night, step outside and take a look at that star and look at it for a few minutes, and you'll notice that it doesn't look as sharp as the stars around it. It's actually kind of blurry. And it's because you're looking at this intense star forming region. Now, this is 1,400 light years distant. So back to light years. This means that your view of this nebula is 1,400 years in the past. And over that time period, you wouldn't see too many changes. I mean, that's rather short in the lifespan of this stage of stellar evolution. But you're looking at an object that's also 25 light years in diameter. So it takes light 25 years to get across this object. And this is a fantastic example of star formation as we see it today. So let's show you another stage here. So we talked about star formation using the Orion Nebula. But let's switch over to looking at an object called the Messier 46 Open Star Cluster. The Messier 46 Open Star Cluster is what the Orion Nebula is largely going to look like once all that hydrogen gas has been blown away. Give me 1 second here. So, looking at the Messier 46 Open Cluster, I talk to myself too, so just bear with me. Usually I'm surrounded by a lot of people in the observatory, and I like to feed off of everybody. I'm actually sitting right now in my woodshed so I don't get rained on with all of my gear out here. In a little bit, I'll turn on my phone and show you how ridiculous my setup looks like out here. And my neighbors, who I can see them looking out the window next door, are probably wondering, who the heck is that guy talking to out there in his woodshed? So what you're seeing here is the Messier 46 Open Star Cluster. You're looking at a cluster of about 3,000 stars that have all formed from the same molecular cloud. These stars are all young stars. These stars have all formed from the same cloud, so they're all sibling stars, and they're all the same age. Now, these stars are all less than 500 million years old. And this is what the Orion Nebula will look at. This is the second stage of stellar evolution as we see it today in star formation. Now, when you're looking at this, you're going to see a lot of stars, and you're going to say, wow, that's awesome. But there's a little Easter egg in here. You know, no pun intended. You know, I understand Easter's this weekend, yeah. But there's a little green circle, almost looks like a little smoke ring in your view. And what you're looking at right there is the same thing that Sean was showing us earlier, but just in a different object. This is the formation of a white dwarf. This is the death of a low mass star. But how come we're seeing a low mass star, which has a lifespan of about 5 to 10 billion years, dying in a cluster of stars that is really young? It's kind of an interesting question. It's somewhat of an anomaly, right? One of the rules that we have at Frosty Drew, especially with our interns, is we tell everybody, when you have a problem, don't start looking for solutions in the real complicated area. Always start in the low-tech side, the simplest part, because the simplest solution is where 90% of your answers will lie. And in this case, the answer to this situation is that that star that's dying is not actually part of the cluster. It's in between us in the cluster, and it's just in our line of sight. I mean, think about it again. We're talking about the Milky Way galaxy here. Everything we're showing you tonight so far, minus the galaxy pictures, is in the Milky Way galaxy with us. 200 billion stars. So the possibility of a star being directly in our line of sight to another object, that probability is pretty high. And that's what we're seeing. So take note of that. But when we're looking at this cluster, try to think about a lot of things that are happening here. So most of the stars that we see when we look at it like this, and this is what the telescope would see tonight if we actually had the telescope on it, and this is on our list of objects to observe tonight. This object And when you see me click in here and you see things moving, I'm moving through different frames that we've captured. And this is roughly about a 30-second exposure at very high ISO. These stars you see are all the high mass stars. The low mass stars are just not as easily visible to the naked eye. And when looking at these stars, what you're looking at is a loose gravitational balance or equilibrium. You're looking at all these stars being held together by their own gravity. Now, being that it's a loose gravitational balance, this cluster over that 500 million year period of its existence will be interacting with molecular hydrogen clouds. It'll be interacting with supernova remnants. It'll be interacting with the demise of small to mid-sized stars that create these slowly expanding gas clouds that used to be their outer envelopes. All of these interactions, these things that are happening, disrupt the gravitational balance of the cluster. And eventually, stars on the edge of the cluster, it's almost like a vibration, they start to detach from the cluster. And most of the time, stars will detach with the stars that are right next to them, and they'll stay gravitationally bound to each other for their entire lives. These are where we get our multiple star and binary star systems from, where you have more than one star that makes up a star system. But every once in a while, a star will detach alone. And that's what the sun did. And when you think about all the stars in a galaxy, about 63 to 68% of all stars in a galaxy are binary stars. They have a stellar companion that is part of their star system. It's not just one star. So star systems like the solar system with just one star, the sun, are less common. So the next time you hear about a binary system and 5 or 6 stars that are all combined, and if you looked in the sky, you would have 5 suns in the sky, and you say, wow, that's kind of crazy. Think about it. That's actually more common than what we have here. And I wouldn't say we're like, the friggin' weirdos, but we definitely are the less common. So,
Scott, someone had a quick question, Chris, and he wanted to know about the Atlas comet, if that's visible.
Yeah, so Comet Atlas it's fabulously visible right now. And I'm going to put up a data set of Comet Atlas from this past week. Give me a second. And I'm actually going to show you something too right now that actually is one of the really great things about being able to live stream like this, is because everything we do out here, we're collecting data. Either we're collecting data from our telescopes live, or we collected it earlier in the week, or we collected it earlier today, all of which gives us the ability to manipulate this data in true geek fashion. So Comet Atlas. Comet Atlas has been putting on a fabulous show for us over the past maybe month or so. And what's really great about Comet Atlas is that we didn't expect for it to be so awesome. Comet Atlas was supposed to be kind of dim, so its actual designation is Comet C 2019 Y4 Atlas. And we expected Comet Atlas to be dim. We're talking big telescopes like the one at Frosty Drew would see it, but outside of that, not so much. But then the comet experienced an outburst back in February. Now, an outburst happens when the nucleus of the comet, we're talking about a piece of rock that's upwards of maybe a mile in diameter. It fractures. And it fractures underneath the intense pressure of the solar wind. And that solar wind, it's heating up the comet. You got all these charged particles slamming into the comet. I mean, the comet is really getting, beat up. And it starts to heat up, and it starts to outgas. And all the volatile compounds on a comet, we're talking cyanogen, diatomic carbon, all of these elements start to heat up and outgas. And that's where we get, these comet tails from and all that great stuff. But sometimes the comet just can't withstand the intense interaction with the stellar wind, and the core or the nucleus of the comet fractures and breaks open. And when that happens, a substantially high concentration of material in the comet becomes exposed to the stellar wind, or the solar wind in this case, and that causes the comet to begin outgassing at a much higher rate than it was initially doing, and causes it to brighten substantially. And that happened in February. And when that happened, the comet became one of the brightest comets in the sky. So you guys see the comet? Is it up?
Not yet. There it is.
So this is Comet Atlas. Comet Atlas is it's currently in the constellation Camelopardalis. I'm sure all of you guys have heard of the constellation Camelopardalis, the camel leopard. Another way we can think of this is a giraffe, you know, like the spotted leopard or the spotted camel, spotted like a leopard. So Camelopardalis. It's just above the constellation Ursa Minor at this time of the year in the night sky, which puts it in a fabulous point for us to see. Now, perihelion of the comet. Perihelion is when the comet reaches its closest point to the sun. Perihelion with Comet Atlas will happen on May 31st. So we have months of fabulous viewing ahead of us of Comet Atlas, with the exception of one problem, is Comet Atlas has already fractured once, causing it to outgas substantially. So this comet may actually not survive its passage with the sun. Now, unlike a lot of short period comets, you know, comets that come through the solar system and swing past the sun once every couple years or once every, 50 years, Comet Atlas is a long period comet. And we're talking that, like, I believe it has an orbital period of just under 6,000 years, in the 5,000 year range. I'm not positive on that. I have to look that up, but I do believe it is. So this is a long period comet. So we're never going to see this comet again. And this comet doesn't come around the sun all that frequently. And it's possible that this is its first passage around the sun, and it may not survive it. And some recent data sets I have seen of Comet Atlas have showed us that Comet Atlas may actually have fractured again to the point where it actually is now in multiple pieces. And if that's the case, we'll get a very bright view of it, but it's going to last for a very short period. And we may miss out on what could have been a real fabulous time of this comet. So now, looking at this image in front of you on the screen, you're going to notice there's a lot of stars. The comet is the green glowing object that's relatively in the center. Now, the reason it looks green is because you're looking at the diatomic carbon, the cyanogen in the comet that's outgassing, and a very thin atmosphere has formed around the comet's nucleus. So again, your comet nucleus, we're talking, 1 to maybe 3 kilometers in diameter. This thin atmosphere that forms around the comet due to outgassing, called a coma, that grows huge. 2 weeks ago, Comet Atlas's coma was half the size of the diameter of the sun. That's crazy. That means that Earth could easily fit inside the atmosphere of this comet. It's not going to, but it could. So from this data set covers about I think it's about an hour of data collection right here. And I'm going to show you now a video of the comet over that period of time, and you'll be able to see the comet's movement in the sky. So give me 1 second to switch over. And comets move quite quickly. It's unlike looking at stars, which all over the period that we see them move together. They don't actually move together. It's called proper motion. All stars have separate motions in the galaxy, but these happens over periods of hundreds of thousands of years. We don't see them over a period of a night. Or Comet Atlas, over the period of an hour, you'll notice that it has a substantial change in position. And that's pretty cool. So here is that data set that we were just looking at, or those collection of images, combined into a quick video. This is the motion that you'll see over an hour of Comet Atlas. You'll notice, actually, you see that one image? There's a satellite that passed through. You'll notice real quick, like the line. After I'm done, I'll bring that image up and you can actually see what it looks like how many satellites we're catching in our views. But take a look at Comet Atlas in this live video, or this live view of it here, this video. You'll notice that as it relates to the stars around it, Comet Atlas is moving towards the left side of your view. This is how much the comet moves in the sky over the period of 1 hour. Not only does this make capturing a comet tricky, it also gives you a really interesting point of view of how comets move around the solar system. Another thing to think about with a comet, any comet in the solar system, when a tail forms on the comet, the tail is a product of the comet interacting with the stellar wind. It is not a product of the comet's movement. A lot of people, when they think about comets and their tail, they think about the comet moving across and leaving the tail behind it. And there is a circumstance where that happens, but largely it doesn't. The comet's tail is a product of the comet encountering the solar wind, which is constantly moving out from the sun across the solar system. So the comet's tail always points away from the sun. So as the comet approaches the sun, the tail is on the opposite side of the comet as the sun. But when the comet swings around the sun, the comet's tail always stays on the opposite side of the comet as the sun. And then when the comet starts to leave the inner part of the solar system, the comet looks like it's chasing its tail because the tail is on the opposite side of the sun. And that's pretty interesting. On the unique case where a path or a debris field is left behind the comet that's actually visible, that's called an anti-tail. And though we don't always see it with a lot of comets that come through, there was a comet called Comet, I think it was L4 Pan-STARRS, back in maybe 2012, that had an anti-tail that was almost 10 degrees in length. That was awesome. Now, I mean, you're probably thinking, okay, yeah, whatever, 10 degrees, so what? But for me as a geek, that's a true geek out right there. So let me can this video real quick. And I'm going to show you that frame of that satellite passing through. I mean, it's kind of funny when we're observing satellites on a regular basis. At Frosty Drew, the first satellite that we look at, everyone's like, oh my God, that's a satellite. I can't believe it. That's amazing. But we see satellites so frequently, then, an hour later, we point out a satellite and people are like, oh yeah, it's just another satellite. I mean, they are everywhere. And what it comes down to with looking at satellites in the telescope or just in the sky, just naked eye, is the observer needs to be in shadow or in nighttime where the satellite itself needs to be in daylight. Because we're not looking at light that's emit from the satellite. And this applies to the ISS as well. We're looking at light that is emit from the sunlight that reflects off the satellite. So let's see here. That's not it. Give me 1 second. Thought I had it, but that's not the one I wanted. So here we go. Let's see. I'm going to find the satellite for you guys. And if anybody has anything to add, by all means. And Derek, if you're ready to present too, I'm all up for switching over after I show them this image of the satellite with the comet.
So it's clearing up here, so I'm going to set up to do, see if I can get the telescope up and running. But if that falls through, I was going to show the couple of images that I picked off.
So you're about to get a little bit of jealousy from me on that because it's still raining here.
Well, that is
we
spread out.
We had debated lying to all you guys and just playing back these data sets and being like, oh yeah, it's clear over my house. I don't know about you down the street from me, but it's clear here. But we figured a culture of lies just begets more lies. So we weren't going to do that, right? Let's see here.
Scott, someone had asked a question. Seems like a quick one. When it comes to telescopes, can some of these be seen with a 400 millimeter lens?
Oh, yeah, absolutely. Okay. I mean, I guess what it comes down to is what you're asking. If it's anything that we've looked at tonight, definitely. Most of these objects we're looking at here are what I would consider very bright, very easily observable objects. So a 400 millimeter lens on a camera would pick them up perfectly. I mean, you're going to have to do long exposure. You're going to have a clock drive. But if you have a 400 millimeter telescope, like that sounds to me almost like maybe one of the 114 models, the Celestron has them, the Meade has them. that you would be able to see all these objects with that as well. Let's try one more time here to get this object up where we can see it. And if I can't, then I'm just going to give up and hand it over to Derek, and you guys can cry about it.
Working on getting mine going too. It's cleared up here.
Oh, are you really?
Yep.
What's up with that, huh?
I'm actually trying to get over to the Comet right now.
Hey, Scott, we had a question from Chris, and he wanted to know if the Starlink satellites are bugging you guys.
So that's a good question, Quiz, because the Starlink satellites are raising a lot of concerns. Now, we're scientists. We go with the data. And I've seen a lot of the information that's put out there, and I'm going to have to say right now that a lot of it is rhetoric. And though I do see areas where there's a concern, as of now, I'm not going to say that from an observational standpoint or from a visible light data collection standpoint, they're a major problem. I have seen some pictures of the Starlink constellation passing through some, it collects data collected from, say, Mount Lemmon out in Arizona and possibly some other observatories. But that's a very specific circumstance, and that is easily avoidable. Where the problem exists that I've seen from a scientific perspective is radio. So radio astronomy is a huge piece in what we're learning about the cosmos. I mean, we have a lot of flexibility when it comes to radio observation and radio data collection. And a lot of things in the cosmos happen in the radio part of the spectrum. Pulsars, things like observing black holes. I mean, that image that we saw of the black hole this past summer 2019, that blew everyone's mind, that was a radio image. All of these satellites communicate with radio. So that would be almost like trying to have a visual observation with a strobe light shined right into the front of your telescope. So that's where the problem exists with the Starlink constellation. If we're talking about putting up hundreds of thousands of Starlink satellites, then yeah, we could run into a problem with it in the visual spectrum. But until that happens, I'm not gonna bang on it. So it's all you, Derek and Sean.
Still working on getting going. Getting there though. I run my telescope completely remote from inside. So right now it's going through its plate solving, so it can kind of orient itself in the sky as to what stars are what, and what's up, what's down, what's left, what's right, etc. So bear with me a little bit while it works on that.
Sean's using big words here because he wants all you guys to feel really special.
Someone did have another question about one of the pictures with the nebulas. It said, did the stars visible in the belt get formed from the nebula?
They did not. So ultimately they were formed from a nebula. All stars that we see in the galaxy today largely formed from a nebula at some point, though they did not form from the Orion nebula that we were looking at earlier.
Okay.
Derek, are you rocking over there?
His
Doesn't
screen
look like it.
back.
Yeah.
Oh,
There he is.
in person.
I could throw up another set real quick while you're getting orientated, Sean.
Yeah, I don't have all the fancy stuff that Sean's got, so I've got a manual setup process on my end.
Sean, see, Derek's doing it like the way they did it back in Ptolemy's day.
Yeah.
If you want, I can share my screen.
So I do have a picture that the gentleman that asked about the 400 millimeter lens might be interested in. I have a picture that I took with a 135 millimeter camera lens on an SLR style camera. So let me see if I can share that, and then we can talk about that for a minute. A window. everybody see that?
Yep.
Okay. So this is the Andromeda galaxy.
lovely.
Taken with a 135 millimeter prime camera lens, and you can see the two companion galaxies. One is here, and then one is basically perpendicular to the axis of the galaxy. And that's a field of view that's almost 5 to 6 full moons. Well, sorry, the field of view is much wider than that, but the object we're looking at is about 6 full moons across, just to give you an idea of how large that is in the sky. And when we look at the Andromeda constellation, you can actually see this. It is, faintly visible in a dark sky, and that light is coming from 2.3 or something million light years away. So it's quite a ways out there, and it is the farthest object that we can see with the naked eye. And I haven't done astrophotography for a while, so everything I've got is pretty old, but getting back into it now. So
I have an image right here that at 430 millimeter. If you'd like me to throw it up.
yeah, go for it.
All right, this is Bode's group right here. 1 second. Now, Bode's group is one of the groups of galaxies that are, quite close to the Milky Way. We're talking at a distance of about 11.85 million light years distant. And there are 2 galaxies here. You have M81, which is on the bottom spiral galaxy in your view, and then M82, which is the galaxy that you see at the top that looks like a very thin galaxy. This image was captured at 430 millimeters with a 72 millimeter refractor telescope. So the focal length was 430 millimeters. And Bode's group is really a fabulous piece for us. This is quite bright. It is naked eye visible, and you're looking at a starburst galaxy. That galaxy on the top, and Messier 82, it's also known as the cigar galaxy. Don't smoke cigars, by the way, especially on the Frosty Drew campus. But if you're home, by all means. But the cigar galaxy is a starburst galaxy. That galaxy has recently interacted with another galaxy, and as a result, it is very disturbed, and all that molecular hydrogen is mixed together, and we're seeing a substantial amount of star formation happening in it. Messier 81, which is the one on the bottom, also known as Bode's galaxy, you can see the spirals on it. You can see the bar in the center. You can see that bright central galactic nucleus. And we're looking at this galaxy somewhat off axis. It's not on edge and it's not face on. We're seeing it somewhat tilted. And I'm gonna stress again, this is 11.85 million light years distant. So this view, which we captured earlier this week, was from 11.85 million years ago. If you want to see it tonight, you got to wait 11.85 million years. And that is close to us. Here is another image that I captured of a galaxy group with this at the same focal length. And this one's called the Leo triplet. Now, the Leo triplet is comprised of a series of, let me get it up here real quick. Hang on, open it up. I'm on Linux right now. If I was on Windows, I'd be crying. There's my political statement of the night. Okay, so this here is, hang on 1 second. Stay in slideshow mode, please. There we go. Why don't you stay in slideshow mode? All right, so this image here, this is the Leo triplet. And there's a lot of galaxies in this image, but there are 3 very bright galaxies you see here. And these galaxies are also part of a galactic grouping. Now, like we were talking about binary stars earlier, we were talking about molecular hydrogen clouds, we're talking about open star clusters and gravitational influences. Well, guess what? Galaxies group together as well, and they are held together by their gravitational influences too. The Milky Way galaxy is part of a group of galaxies called the local group, which is also what the Andromeda galaxy is part of. And the local group is comprised of 3 large or very stable or primary galaxies, the Milky Way, the Triangulum galaxy, and the Andromeda galaxy, with the Andromeda being the largest and the Triangulum being the smallest. And then a series of satellite galaxies that surround the larger galaxies. The Milky Way has them. Andromeda has them. As you saw in Derek's photo, you would have noticed there's a couple of them in there. And these galaxies are all held together by their combined gravity. It's an equilibrium, but it's not a stable equilibrium. These galaxies do approach each other and they will combine. Now, the local group is also part of a much larger galactic cluster called the Virgo supercluster. And the Leo triplet, which we're looking at right here, is part of the Virgo supercluster. Now, if you were to look at the night sky and identify the tail star of the constellation Leo, it's called the nebula. One of the stars in the constellation Virgo looks like a Y, so one of the end stars is called Vindamayatrix. It's near the nebula. And then the constellation Coma Berenices, which is Berenices' hair, they're all very close to each other. If you take those 3 points and form a triangle, in the middle of that triangle is the center of the Virgo supercluster. And in that area of sky is thousands of galaxies that are visible to our telescopes and cameras. That part of the sky passes over the zenith from our location in the month of May. And as a result, we call May Galaxy Month amongst the geeks. Now, I know Sean and Derek, I'm not sure. I do believe that you guys had done some work with the Leo triplet.
A little bit. That's one on my list. I got to reshoot. I've been doing this for several years now, so I have some poor data that I've collected over the years, and this is one of them. So it's one I want to get back to with my new setup that I'm much more confident with.
Sean sends me some of his poor data sets. And I'm like, you know, if you just release this to the public, people would freak out because they would be like, oh my God, that's amazing. So you're listening to a perfectionist over here. Just disregard him. His images really are quite fabulous. And this summer, when we open Frosty Drew back up, in the Science Center, we are running galleries. And we're going to be showing the works of our astronomers, the works of a lot of the night photographers that we work with. We're going to put a shout out right now to James Iverson Crouch, who is a fabulous night photographer in the area. And we've been begging him to do a gallery at Frosty Drew. Stop by and check out the works of these amazing astrophotographers because it'll blow your mind. You'll walk through that room and you'll say, what is this? How come I don't see this stuff on the news every night? How you doing over there, Derek?
I'm good.
You ready to go?
Well, we're getting there. I was pulling up my Leo triplet data from a couple years ago. If you wanted to,
yeah, throw it up. I'm going to relinquish.
Talk about that real quick. So this is let's see. I just found it. To excuse my slow internet. It's a large picture. And then I just got my camera in focus, so maybe we will be able to do some live views here in a moment from my scope. Sean might be further along than I am.
Mine's working on autofocus right now.
Okay.
So far, not so good.
Apparently the scene is terrible. The stars are dancing all over the place tonight. Yeah. I was like, why is it moving so much? I'm in a building. Oh.
You know, it's kind of really easy to call in sick when you're an astrophotographer and astronomer. All you got to do is be like, my camera's dewed up.
All right.
Someone had a quick question about Saturn, when the best time to view Saturn was.
Whenever you want.
Yeah, that's Sean. They're right there. So anybody
so
want to
actually,
take that?
I've got a good answer for that one. This summer's probably going to be like prime planetary viewing because we've got Jupiter and Saturn are getting real close together in the sky. Mars is going to be coming back around late in the summer. So we're going to have like 5 planets in the sky at the same time. It's going to be pretty awesome. Some of them will only be visible with a telescope, but Saturn and Jupiter are going to be hanging out real close to each other all summer. So I've got my Leo picture up. As I said, it's a little over processed and it's blue, but it is something worth talking about, I think, because it does show some detail. So let's see if I can figure this out. Present. All right.
Oh, lovely. Look at that.
So at the top is NGC. Oh, I forget the 4-digit designation for that NGC. And then the bottom 2 objects are M65 and M66. In a modest telescope, the 2 bottom galaxies are pretty easily identifiable. And the NGC that's at the top of the frame there really only comes out in photographs, as I've found. But you can see the different structures of M65 and M66 there. One, kind of has a very defined spiral shape, and then the other one has clearly gone through some sort of interaction and is starting to lose the structure of its arms. So,
I mean, an interesting thing to think about here too is that though this galactic grouping is part of the larger Virgo supercluster that we're part of, this is still about 35 million light years distant from us. So if you were there looking back at Earth, you would see a period on Earth tonight that was almost 20 million years before humans arrived. I mean, that's pretty cool.
Definitely very cool.
And when you think about, so as Derek was mentioning, that the NGC galaxy at the top, which is definitely a bit perturbed, that galaxy is NGC 3628. That's similar to the Milky Way galaxy. What you're looking at there is a galaxy on edge. So when you look at some of the galaxies on the bottom, especially the galaxy on the left, you'll notice that you can see some of that spiral structure. The galaxy on the right, you see a little bit of it because it's tilted from our point of view. But the galaxy on the top, we see it on its side. And when you're looking at a galaxy face on, like you would M51, the whirlpool we were looking at earlier, or when you think about how the Milky Way galaxy looks, you get those spirals, you get the bar, you get the galactic nucleus, you get that great view. But if you flip it on its side, you pretty much just get that line with a bright central bulge, and that's the galactic plane you're looking at. And the Milky Way galaxy we've recently discovered is warped similarly to how we're seeing the warp in NGC 3628 in this image. And that warp raises a lot of questions. What's causing it? Is that warp created by us interacting with the Andromeda galaxy's halo, which is much larger than what we see when we look at the Andromeda galaxy? Or is the warp a product of us assimilating or absorbing? I like to use the word assimilating because I love the Borg, but absorbing some of the satellite galaxies that are around the Milky Way. One galaxy in particular, the Sagittarius dwarf galaxy, we are absorbing right now. And that could be a very large reason why the Milky Way's galactic plane is currently warped. That was me, totally just shysting and shanghaiing Derek's presentation. I love to take over the camera because, that's me.
It's all good. It got me a little further in setting up my telescope, which takes longer as a manual process. And since it was cloudy earlier, I couldn't do it before this session. So I have to step away and go twiddle buttons and then come back. So, but that was the Leo triplet. And we'll stop sharing and turn it back over to whoever.
Sean, you got anything, or do you want me to continue?
I'm working on getting my Leo triplet up. I didn't realize, but I actually took some data with my RASA.
See, this is the evidence part of what I said earlier.
Yeah. It's not processed, so I'm doing that. I'm processing it real quick.
Yeah.
But it's a little rough around the edges. It's got some halos and stuff in it, but working on it.
You know, most of us do our processing work, pre-processing and post-processing data reduction in our workflows during the week in the comfort of our office. Sean waits until we do a live stream.
Yep.
And that's awesome. I'm not necessarily knocking on Sean for doing something wrong here. I'm criticizing him for being a perfectionist.
Hold on, let me get it into this PowerPoint.
If you want, I could jump on real quick if you like.
Right here, almost. It's just got to download it from Dropbox. All right. Let me see. Let me try and present. All right. You see that?
Yeah, that's beautiful.
Yes.
Look at that.
Yeah.
So
Fabulous.
you can see some halos around the outside. I don't think they calibrated this with flats, so there's my issue. It's actually a lot less pronounced in this slideshow than I thought it would be, because on Photoshop on here it's pretty wild. But anyways, I mean, you can see a lot of the dark lanes and we call it the Hamburg galaxy, because it kind of looks like a Hamburg right in the middle. You get some of the dark dust lanes and some of the galaxies down here too. My camera is a black and white camera, so I use filters to add in the color. So whatever I'm shooting, I have to take either red, green, blue, and then each as a separate channel, and then a luminance layer to get the detail, or I'll shoot hydrogen alpha, oxygen, and then sulfur, and then put those all together. So I have to take, at a minimum, 3 separate images. So that's usually 3 nights in a row if we get good weather, 3 nights of work that I have to put in to get an image. You get some funny artifacts in here, like due to my telescope design, my camera mounts right on the front. So all my cabling runs right in front of the front lens on my telescope. So you get these weird artifacts around some of these bright stars. Like you get spikes out from the center and then from the side, but it's usually not too bad. I think it's some small galaxies in the back here too. That's all I got to say about this. I don't have much to say.
Well, people on chat are really liking that one. You got some smiley faces with hearts for eyes on that.
Yeah, you know, if you look at this image and kind of turn it upside down, it looks like you're looking at a face.
Yeah.
I mean, we're talking about serious pareidolia here, but it does. I mean, when I look at it, I almost feel like it's the universe looking back at me.
Yeah.
As ridiculous as that is.
Let's see, can I rotate?
As we move into our last half hour of our session here, I have some live views of the moon that we can kind of get out there if you guys would like to see them. But before we do that, I have one more image of a galaxy here that I might want to throw up. Let me just see if I can, put up. Yeah, I don't think throw up's the right term to use at this time in the world, right?
Please don't throw up.
Second here.
There we go. I made it into a smiley face.
Did you flip it over?
I did.
Yeah. Good job. Let's do this.
Thank you. Thank you.
All right. So, give me 1 second, and I'm going to throw up the image of the Sombrero galaxy. This again is an image that was captured just recently. Let's see here, get this over. I know. Put that out. All right, so let me see if I can share this. So the Sombrero galaxy is found in the constellation Virgo. And this was on our list for tonight to observe as well, though the Sombrero galaxy has very interesting structure to it. Unlike most galaxies we look at, the Sombrero has a very active dust lane, which is that dark line that you see that kind of moves through the middle of the galaxy along the galactic plane. And it moves right along the edge of the galaxy. And that is a very, it makes this galaxy, so I don't know why they named it Sombrero. I think it, it looks like a hat to somebody, but I see it more as a galaxy with a fabulous dust lane on the edge. But this galaxy has some interesting things about it. One really interesting thing about this galaxy is its distance. So this galaxy is about 31 million light years distant from us. It's on edge, so we're looking at it from the edge, but it is slightly tilted so you can see just a little bit across the galactic plane. Though the stars in this galaxy are slightly disturbed, and you get what appears to be a bulge around the entire galaxy. Now, most galaxies, especially all spiral galaxies, have what we call a halo. A halo is a transparent bubble of stars and objects that surround the galaxy. They are the oldest objects in the galaxy, and they are the furthest objects from the center of the galaxy. The Milky Way galaxy has a halo as well. It's roughly about 33,000 light years distant from us. But the halo of the Sombrero galaxy, it looks like it could possibly be visible. And this is a really fabulous object to look at in a backyard telescope. And this is very visible through the entire spring over New England or the Northern Hemisphere. Now, I'm going to switch over, unless Derek or Sean has something they want to show real quick.
I'm trying to get focus. I'm on the Comet Atlas right now.
Oh, you actually have clear skies?
Yeah. Oh, yeah.
Oh, yeah, that's nice. Put it up. Let's see it.
Hold on.
Yeah, see, we don't have that here. We don't get nice things over here.
Trying to get some the focus. The autofocus isn't running correctly because I think there's too much wind.
That is something that I don't have here in Providence is wind. But I have clouds and I have rain.
It's very windy right now.
And I also don't have any scotch in my glass.
That's a problem.
That is a problem.
All right. Let me get
Hey, Sean or Scott, quick question. Christina wanted to know, well, Sean, what did you mean when you said you filter for hydrogen and other gases? Do each of these gases have a different color?
Yeah, so Scott explained earlier the hydrogen alpha wavelength is in the red spectrum, oxygen 3 is in the blue spectrum, and sulfur 2 is in the green spectrum. So each of that, you use the filters to isolate these different wavelengths, and you don't actually necessarily have to map those wavelengths to their respective colors or the appropriate color. You can use them and map them to whatever color you like, color channel you like. Each of us uses different software to post-process, but I use just basic Photoshop, and inside there you can make an RGB image and then plug each of those colors, which will represent a separate image, into red, green, or blue, whatever you like. And those color combinations end up making different details pop in the end image. So here, for example, I'll bring up an image of the bicolor image I had done on the Veil Nebula last summer, and talk about that a little bit. So this image I did is the Veil Nebula. That's a summer object in the constellation Cygnus, It's a pretty cool one to observe. You usually have to use some sort of high contrast filter, or an oxygen filter helps bring a lot of that detail out. But this is a bicolor image using hydrogen, alpha, and oxygen. So the blue you see there is all the oxygen data, and I mapped the oxygen to the blue, and the red, orangey colors you see are hydrogen alpha. So each of those were a separate image that I took and processed in separately in Photoshop. And if you took them apart, they would look like two black and white images. And then, I mean, you can keep them like that. Some people do. Some of my earlier pictures I showed were all black and white. They were just the single color. But then you can put them at really cool bicolor images, or people even do tricolor. You could add in sulfur and put that in the green slot, for example. But that's what I mean by doing separate channels. All right.
And a lot of good comments about that one there, Sean.
Oh,
Yeah, the veil is a beautiful object, and that's a fabulous capture of it.
thank you. Yeah,
Beautiful.
that was that's one of my favorites. I was actually working on a mosaic last summer of the entire veil structure with my RASA. I didn't finish it. I got quite a bit of it done. So this summer I'm hoping to be able to finish that.
So if you guys take a look real quick at Jessica over here, she's the Stargazing Night Supervisor. That girl right next to her is Unity. And Unity is the youngest team member at Frosty Drew. She began on the astronomy team when she was 4 years old. If you come out to Frosty Drew during the summer months, you'd be able to find her operating an 8-inch Orion XT8 telescope on the lawn in the observatory courtyard, and she'd be talking about the objects that she's looking at, things like the star Vega, things like the binary star Albireo, and all the fabulous objects that you can see in the summer triangle. And she is a great example of what it means to really want something. When it comes to working in physics or working in astronomy, there's definitely this stigmata that you need to be really smart or that you need to be special. That's nonsense. If someone's telling you that, you need to just stop listening to them. You just need to want it. I mean, this is for everybody. And I meet a lot of people in my daily life where I wonder, I'm like, why are you not working in this? Because you are so great at it. And the first thing I hear is, oh, I can't hack the math. Or, oh, that's not for me. I'm not that smart. But that's nonsense. All you need to do is want it. And if you want it enough, it's there for you. And if you guys want to join the Frosty Drew team, we have an internship program that we run during the summertime. And we also have a volunteer program that runs during the summer and all year. And anyone who wants to be on the team can apply. If you are under the age of 16, then your parents need to apply with you. And you guys will volunteer together. So if you have any questions about getting involved with Frosty Drew, you want to make sure that you write an email to astronomer@frostydrew.org. And Jess or Lindsay will post that into the comments or the chat stream so you guys can get it. And Unity, do you have anything you want to say?
No.
Yeah, usually she just doesn't stop talking. Anyone who's met her at Frosty Drew will vouch for that. But I think that, and also take note how she wears her earbuds. That's all Unity right there. So, and just so you guys know, Unity wants to be one of the first people to go to Mars. And Unity is 10 years old. Actually, her birthday is tomorrow. She turns 11. And she is part of what we call the Mars generation. The Mars generation is anyone pretty much between the age of 5 and 20 years old. In the year 2030s, probably the late 2030s, we're going to be sending the first real astronaut mission to Mars. This is going to be a mission comprised of individuals from countries all over the world, including the United States. Probably about 10 people will be on this mission, and these will be the first humans to ever visit another planet for the first time. On this mission, one of those astronauts will be the first one to step off that spacecraft and put their boots on Mars. And that'll be the only human in the history of our species to set foot on another planet for the first time. Those 10 people, that first person, they're walking around on Earth right now. They don't know it's them, and they're in that age range. That's amazing to think about. When that day comes, I'm going to raise my hand. I'm going to say, I want to go to Mars. I want to go on that, but I'm going to be old. They're going to laugh me out of the room because I'm not going to be able to do that at that age. But anyone in that age range is going to be the perfect age to do something that awesome. So aside from having to ask yourself if that's something you really want to do, I understand there's a lot of pressure in that statement. But if you're having a bad day and you're in that age range, you feel like that the world's coming down on you, remind yourself that if you want to, you could actually walk on Mars one day. And though I'm sure there's dozens or hundreds of things that make you special in your own right, that alone, in my mind, makes you fantastic. So seize that opportunity and walk on Mars. And maybe Unity will be part of that, and you'll be a passenger with her on that 6 to 9 month mission to Mars, 6 months there, and then 6 to 9 months back. What do you think about that, Uni? You going to go to Mars?
I want to.
Yeah, so do I. Doesn't mean I'm going to. But that's not me putting you down. I think you can do it. So, Sean, you got Comet Atlas, or do you want me to throw up some lunar images?
I did, and then I got some nice gusts of wind. And it's coming back. I don't know. It's up to you. You can throw up.
Sean's calling out sick.
Pretty much. I can show you if you want. It's a nice.
Yeah, throw it up. Let's see it. Let's see what you got.
It's a nice star trail image. All right. Check out the star trails.
Oh, nice. That's excellent tracking, though I can easily make out where the comet is.
Oh, yeah. So
it's the object that has the blur around it.
Yep. So that's it. I'm taking looping exposures, so they should come and go. My guiding, this is my guiding, and it was going fine, and then we got some wind, and now it's taking off. So it's getting worse. So if you want to throw up some lunar images, you can do that.
Definitely. So earlier this week and last week, before the full pink moon occurred, which was Tuesday, we did some data capture for some images of, high magnification images of regions on the moon. Now, the reason why we're not looking at the moon tonight is because of two things. One, it's raining where I am, and where Sean and Derek are, the moon hasn't risen yet. Tonight, the moon's not going to rise until after 10 o'clock, which is beyond the end of our session. Though, when you're looking at the moon, the best time to look at the moon is largely during anywhere from 60% all the way up to maybe 89% waxing gibbous. That's because that sunset line, we call it the terminator, which is where the sunlight ends and the shadow area begins, it sits over all the best regions of the moon. And along that sunset line, the terminator, is where we see the most accurate representation of the rigorous, detailed lunar terrain, because shadows are cast and we get a depth of field in our view. Now, these images are all captured largely along that region. Now, these aren't images, these are videos. This is what you would look at. This is exactly what it would look like if I had the camera on the moon right now in the telescope. So this image I'm going to put up right now this is Tycho Crater. Tycho Crater is one of the craters on the moon that is part of a period that we call ray cratering. Now you're going to see a lot of craters. You're like, wait a minute, Tycho Crater, which one's that? There's craters everywhere. Tycho Crater is the crater that's on the bottom right that has a substantially higher amount of detail in the rim around the crater than a lot of the other craters you're seeing. Like, it looks a little sharper. You can see that there's definitely stepping and buildup on the inside of the crater wall. You'll also notice that in the center, there's a little peak, a little mountain in the middle, where a lot of the other craters don't have that. And what you're looking at in that spot is a bounce back kind of like when you throw a rock into water in a pond and it bounces back up from the center. The same thing happens when impacts occur on the moon, large impacts. And they leave that peak in the center. Now, let's talk about this from a sense of scale. That little peak in the middle of that crater, that bounce back, that mountain is taller than Mount Washington. And this crater is about 55 miles in diameter. The crater rim on the outside is substantially higher than the peak on the inside. You're getting into mountains at that point that are more like what you would see along the Rockies or in the Himalayas. And if you were standing inside that crater, you wouldn't say, hey, look at me, I'm in a crater. You would say, you would feel like you're standing in a valley with very large mountains in the distance. And those mountains, that's the crater rim. Now, we can gauge an age of a crater by how sharp and well-formed the crater rim is, the detail that we see in the bounce back, if it's even visible at all, and also any ejected matter that may be around the crater. When you think about the moon doesn't have, so think about the moon and the Earth. So the moon's covered in craters, and the Earth doesn't have so many. But Earth is about, the moon's about 1/4 the size of Earth, 1/16 the mass of Earth. Clearly Earth is the gravitational mass or the larger object here. So Earth is probably getting hit a lot more than the moon is. But where's all the craters? When you think about Earth, we have active geology. On Earth, we are pretty much tectonic plates floating around on a liquid mantle. Lava. The mantle of Earth is largely lava. So the surface is constantly recycling itself. Additionally, we have a very functional, very dense, very active atmosphere that we love it and we abuse it. And that atmosphere constantly changes the landscape. I mean, there's a lot of things on Earth that resurface it. You can test this summer at the beach. Go down to the tide line, stick your foot in the sand and watch the next 2 or 3 wave cycles erase your footprint. Earth is constantly recycling its surface. It's resurfacing. The moon does not have active geology today. The moon's mantle is largely solid. It's semi-molten, so it's like a hot clay. There is no atmosphere on the moon. So the only thing on the moon that resurfaces that lunar landscape is other impacts. And we don't see very large impacts anymore on the moon, like what formed Tycho crater or some of the large craters that you see in the view right here. The type of impacts on the moon we see today in the current state of the solar system are largely just small meteorite impacts, which instead of leaving large impact craters, they slowly chisel away at the surface area and flatten out the craters that are there. Craters that are older have been subjected or exposed to this chiseling for so much longer that they start to flatten out. On the edge, they start to round off and they don't look so deep. Younger craters that haven't been vulnerable to that type of activity for as long tend to have a lot more detail. Now, we're going to switch real quick to another crater right here. I'm going to throw in a view of Plato crater. Now, Tycho crater is on the south side of the moon. Plato crater is in the north. Now, Plato is an interesting crater because it's got a lot of features of both of what we were just describing. Plato crater has some pretty rigid edges, but it's not very deep. Inside Plato crater, there's not a lot of detail. There's not a lot of what appears as recent activity. It's very flat. There's no bounce back peak. Around Plato crater, you can see that you have darker regions and you have lighter regions. Those darker regions that you see are called Maria. Below Plato crater is called Maria Imbrium. And above Plato crater is another Maria. And to the right, you have Maria Serenitatis, the Sea of Serenity. These Maria, when we're talking the ancient astronomers looking up the moon, they used to think that these darker regions were oceans or bodies of water. We saw them on Earth. We have them here. Why are they not on the moon? So we called them Maria, which is a Latin word for sea. But as our optics got better, and as our understanding of planetary geology got better, we realized that we're not actually looking at bodies of water. We're looking at basalt regions or lava beds or lava basins. And to be even more precise, we're looking at the very initial impact craters that happened on the moon. And they happened a long time ago. This is back to that period of old craters versus young craters, that idea of the old craters being so flattened out. These are the initial impact sites. These happened when the moon was still in a state where the core, or the mantle of the moon was still molten. It was still lava. And just the crust had cooled. Very large objects, we call them planetesimals. They're part of planetary formation. And they were very common in the early solar system at that time period. You know, we're talking about 4.3 billion years ago here. Those planetesimals impacted the lunar surface and they broke the lunar crust material that had solidified, allowing for a lot of that magma, that lava, to pull back into those craters. And that lava brought back a lot of the heavier elements like iron that were settling towards the core of the moon. And that iron solidified on the lunar surface. And it reflects less sunlight than the surrounding lunar crust material that we call regolith. And as a result, they appear dark. And even more, from a pareidolia standpoint, they're also what gives us the man in the moon, or the maiden in the moon, or I see the bunny. You know, I don't see the man, I see the bunny. But all of these things are a result of these craters. Now, looking at Plato crater, you'll notice that around it there are a series of mountains. These mountains are called the Montes Alpines, and these mountains are quite large. They are very similar to some of the mountains that we would see in the higher regions of Earth. I'm going to throw up another image here, which is just to the side of Plato crater. And this is a region called Sinus Iridum. Now, Sinus Iridum is a very old crater. It's likely from the earlier period of what we would call heavy bombardment. So heavy bombardment is when the moon was hit with larger objects than we typically see today. Heavy bombardment involves interaction with a lot of planetesimals, a lot of asteroids. And heavy bombardment lasted for a period of from about 4.3 billion years ago up to about maybe 160 million years ago, which is when the ray cratering period happened. And Sinus Iridum is quite large. It looks like a half crater with a substantial amount of crust material up on the upper left side, which would be kind of the northwest side of the moon. And when you're looking at that material, there's a couple reasons why it looks so dramatic in this image. One is because it's along the lunar terminator. You can see that if you look up towards the top left, that the moon kind of fades off. And that's the sunset line you're looking at there. Just beyond it is nighttime on the moon. So you're in a region where you're getting a lot of shadows cast. You got a lot of light on the inside. So you really get a good view of that area. But a lot of that crust material was pushed up in that area by that impact that formed that large basin. One of the recent Chinese lunar landers that landed on the moon, Jade Rabbit or Chang, I think this was Chang 1, landed in Sinus Iridum, and that lander had a rover component which didn't last very long, but it also had an observatory component which actually lasted for quite a while, and it was the first observatory to land on the moon. Now, when you look around the lunar surface, you're going to notice there's a lot of smaller craters. Sometimes you'll notice there's craters inside craters. Like I said, the moon doesn't resurface as quickly and as efficiently as the Earth does. So these craters last a long time. Now, in some of these images, too, we're getting very close to some of the Apollo landing sites. And one of the questions we get a lot at the observatory is, can I see the Apollo landing sites on the moon, and can I see the flag? You got to remember something. The moon is big. It's 1/4 the size of Earth. And it's on average about 236,000 miles distant. I mean, looking at the flag on the moon would be like looking at a mailbox from 236,000 miles away. Our telescope at Frosty Drew can't even look at mailboxes on Block Island, which is just a couple miles south of us. So we wouldn't be looking at those objects with any earthbound telescope. Though you can observe the Apollo landing sites by checking out a mission called the Lunar Reconnaissance Orbiter, also known as LRO. It's a NASA mission, and it's an observatory that NASA had put into orbit around the moon, and its job, amongst other things, is to map the entire lunar surface, which at this point it has, and it has been able to photograph the Apollo landing sites. Though you won't see the flag in the images, you will see the equipment that the astronauts left behind, litter bugs. Gonna leave it at that. And then you will also notice that you can see the footprints that are left behind by the astronauts, including the tire tracks from the lunar rover modules that were used on the missions that had the lunar rover. So check it out, LRO at NASA. And one last thing about this view of the moon, you'll notice that when you're looking at this view, there's a lot of waviness in it. It looks like the moon is like bubbling or floating, or almost like we're looking at it through a fish tank or like a glass of water. And that is a product of Earth's atmosphere. And that is called atmospheric dispersion or atmospheric distortion. And what it is we're looking at all the different types of stuff that's happening in Earth's atmosphere. We're looking at convection, you know, hot air rising, and then as it cools off, it sinks back down and heats back up and rises back up. We're looking at moisture in the atmosphere. We're looking at temperature zones in the atmosphere that are mixing together. All of these processes change the refractive property of Earth's atmosphere. Earth's atmosphere functions as a lens. And what happens is the focus point that our telescopes use to observe go in and out of focus, giving us this wavy feature. Now, this image was captured in monochrome, so it's grayscale or black and white. But if this was in color, you would notice that you would start seeing a rainbow effect around the moon. One side would be a little more red and one side would be a little more blue, and that would be further exaggerated the lower the moon gets in the sky. And that's because that focus point changes the focus point of all the three wavelengths of the visible spectrum, the red, green, and blue wavelengths. And eventually you get to a point where we can't hold focus of the blue wavelengths or the red wavelengths, and we stick to the green wavelengths, and on the edges you get that blue and red glow because those wavelengths are out of focus. And that is a perfect example of atmospheric dispersion. Does anybody on the talk have anything to add about the moon and how we bag on it constantly, but it really is quite awesome?
It's annoying.
See, now that's Sean bagging on the moon. But, and I'm going to just say real quick, we would not be here if it wasn't for the moon. So keep that in mind before you bag on it.
Yes, we should be really appreciative to the moon, even if it wants to block out all the light on every clear night, on every full moon.
And that's a great point too, because it happens. We had a visitor, maybe they're on the chat tonight or on the session, that drove all the way up to Frosty Drew from Brooklyn on the night when the moon was full, and they were like, "Yeah, we want to take a look at the Helix Nebula," and we were like, "It's the full moon. It's going to look like Brooklyn tonight out here." The full moon is cool because it's, you know, you see the moon in the sky, but it is really the worst time to be out stargazing aside from a cloudy night, because the moon is really bright and it overpowers just about everything else in the sky except for the brightest objects. So we're not going to see the Milky Way. We're not going to see galaxies. We're not going to see nebulae. We're not going to see star clusters. And looking at the moon itself is rather poor as well, because the moon is very bright. It's super bright, and the terminator, that sunset line, is not in view. So every area of the moon that we look at is in direct sunlight, and no shadows are being cast, and it just looks flat. So we're down to the last couple minutes of the live stream here. Does anybody have any questions they would like to get in before we wrap it up?
There haven't been any questions right now, just a lot of people saying thank you. This was terrific. They're looking forward to next week. Enjoyed the show.
Awesome. So we apologize for any of the weird things that happened tonight. Like I said, this is a learning experience for all of us. We're taking notes. You probably noticed that I've been typing away on my phone and typing away on my laptop, and I'm journaling just about all the blunders that we've done tonight. And we're going to try to really perfect this process, and we will continue doing this every Friday until Frosty Drew can open again. So this is not a one-time deal. This is going to be a weekly event. And hopefully, I mean, this is spring in New England, so we're not even going to go there. But if we can get a clear night, we will have substantial amount of live views from our telescopes. And if I can do it real quick here, I'll try to patch in my camera, my phone real fast and show you what my setup out here looks like, trash bags and all, to get an idea of the level we're taking this to. Because we really want to have an awesome night. So
Finally
let's
get to see a triplet. Pieces of it.
So I have the Comet back. I ended up losing connection to my telescope, but if you want, I can throw up the Comet.
Yeah, give me just 1 second, Sean.
Yeah. I don't know if am I muted? No, I'm not muted.
No, you're not muted. I hear you.
Yeah, I found the NGC component of the Leo triplet by accident. It kind of drifted into my field of view.
What did you find?
The NGC component of the Leo triplet.
Okay, cool, nice.
Scott just cloned himself, by the way, for everyone watching.
Yeah, now we have 2 Scotts.
Yeah.
Yeah, it's me. All right, hang on 1 second. So I'm going to present real fast here. I'm going to see if I can do this. I'm going to see if I can get my flashlight on while I do it as well. But we have screen, start presenting, and yeah, just do it. Yeah, do it. What's this going to show? This is going to, we're going to kind of can that. I don't know if I'm going to actually be able to get the live view on here right now, but yeah, I can't get it on. So I don't have a view right now to show you of the gear, but I will take pictures and post them. But like I said before, we're going to keep doing this. And this is going to be a weekly thing until we can open again. So anybody else have anything to add? Sean, you want to show anything, or Derek?
Yeah, let me put this up real quick to make sure it even works.
This is kind of like how we do our stargazing nights at Frosty Drew. We say we're going to pack it up at like 10, and then like 1 o'clock rolls around and we're still there.
So this is an image capture tool that I use for capturing images from my telescope as it seems to be wigging out, but that's all right. You can kind of see the image in the upper left of the screen has got the galaxy that we saw in the images before, but this is kind of a live view of my telescope tracking this right now. So that's the NGC component of the Leo triplet. I would try to make it and change settings on my computer, but as you can see, it's barely keeping its head on straight. So that's good to know, because we'll have to do something for next week to make that a little better.
So
cool.
We're hoping for better weather next week, and we are going to be on Facebook putting stuff out as often as possible. Tomorrow morning, the skies will be clear. You guys are going to get out because we have another conjunction of